welcome everyone to another talk at the virtual seminar on geometry with symmetries. Today, it's my great pleasure to introduce Jan Nienhaus. He's a postdoc at Münster, and he'll be talking about Einstein metrics on even dimensional spheres. So, thanks, Jan.
Yeah, thank you very much for the introduction, and of course, thank you very much for the invitation. So today I want to talk to you a bit about Einstein metrics on spheres, and in particular in even dimensions, but well, we're going to get to why I'm more interested in even dimensions in a second. So what is the big question? So of course, you probably know what an Einstein metric is. Yeah? So let's say you have a closed manifold. They say it's Einstein if the Ricci tensor is a constant multiple of the metric. For compact manifolds, or let's say today we'll be mostly interested in simply connected manifolds, compact, closed, with positive Einstein constant. And of course, well, the first two questions mathematicians usually ask when you give them something is, well, does it exist and is it unique? So, of course, for the simplest examples of spaces, say like your favorite space, a sphere, a projective space, existence of Einstein metrics a priori is pretty trivial because you can usually write down the first metric you see and it's going to be Einstein. Yeah, so the common examples, spheres with their round metric, standard metrics on projective spaces. Your favorite space, probably if it has a canonical metric, good chance it's Einstein. And then the next question, of course, well, if you can't solve the problem in general, it may be pretty hard. But the next question is, okay, you have some canonical Einstein metric. Next question you can ask is it unique? And this turns out to be a pretty hard question. Of course, usually the easiest way to solve this is you just find other ones and then it wasn't unique. But of course, if it turns out that it is unique, it may not be very easy to prove. Yeah, so this is the question that we asked today. So is G round unique on the sphere? Yeah, so you may expect this to be true, you may expect this to be false, you may expect this to depend on the dimension. So one thing that's pretty trivial is that if the dimension is small, then it's obviously unique. So in dimension 2, let's assume you define Einstein in a way that the constant has to be constant and not depend on the point. Then in both dimensions 2 and 3, the Einstein condition is equivalent to constant sectional curvature. And of course, then there's only one metric, which of course, yeah, not very satisfying to say, well, it's equivalent to constant sectional curvature. So what happens in higher dimensions? And well, it's been known since the 70s that it's not always unique. Yeah, so let's do a bit of prehistory. So the first non-round Einstein metrics were found in the 70s by Jensen and Böhm. So Jensen found a metric on S4n plus 3 for all n at least 1. And Böhm on S15, which are Einstein, not round, and homogeneous. So the way you do is you take your favorite top fibration, which goes like S3, S4n plus 3, HPN, or S7, S15. That's not a 15. S7, S15, OP1, and you change the size of the fiber. Of course, if you have a fiber of size 1, the sphere in the middle is going to be round, and you can change the size of the fiber, and then you write down the Ricci curvatures, and it turns out, except for the round sphere, there's just precisely one other value that just also happens to be Einstein. Yeah, I mean, maybe there's some very deep reason, but of course, if you write it down and it's Einstein, it's Einstein. Yeah, so since the 70s, it's been known that at least in these dimensions, there's no uniqueness. And okay, these are homogeneous. Yeah, you see by the construction, both the map that fixes the fiber and the map that acts on the base, they both act on these metrics. And it's been also known since well, not quite since the 70s, but since say 82, where Ziller proved these are all. So homogeneous Einstein matrix on spheres. Well, of course, these and the round ones, the round matrix, surely also Einstein. So, okay, you see there in at least half of the odd dimensions, it's not unique, but you also see by Ziller's result that at least in the homogeneous class, all of the examples are in odd dimensions. Yeah, because you know all the examples, they're all in odd dimensions. So for about 10 or 20 years, well, it wasn't known, but it was believed by some people that in even dimensions, maybe you should expect uniqueness. Yeah, I've heard this attributed. Maybe it's not infringing, so maybe I shouldn't say. But for a while, it was open whether there are any counterexamples in even dimensions. And this is the question we're going to ask. Yeah, what happens in even dimensions?
Jan.
Yes.
I have a question. You're talking about uniqueness. Do you know if it is now any manifold that it is now that admit exactly one Einstein metric?
Well, I mean, S3, S2.
Okay.
But yeah, I'm not sure of a highly non-trivial example. Of course, in dimensions 2 and 3, Einstein is equivalent to constant sectional curvature, so they're usually unique.
Okay, thank you.
Yeah, in higher dimensions, you need extra assumptions. So in special cases, you can say something like, okay, if it's homogeneous under some action, if you fix some Kähler structure in the background. But I think in full generality, I'm not aware of an example where full uniqueness is known in dimension above 3.
Okay, thank you.
Yeah, so I will turn to the odd case in a second for a bit, but okay, what happens if n is even? So the most general conjecture that it's always unique in even dimensions does not turn out to be true. Yeah, so the answer was given by Christoph Böhm in 98. So he wrote a paper and constructed Einstein matrix of cohomogeneity 1. Actually, infinite families on all spheres in dimension between 5 and 9. And of course, as you will be aware, the numbers between 5 and 9 contain even integers. Yeah, so in particular, S6 and S8 carry non-trivial Einstein metrics. Yeah, so that's maybe no uniqueness in general. But if you look at the methods, it's not clear whether this is a low dimensional phenomenon, and some geometry thing happens where in low dimensions exceptional things appear and then they just stop, or whether it's just well, maybe there's always these metrics and we just can't find them. Yeah, it's unclear at this point, but at least we have some examples. And of course, you may ask, well, this was 98 and now it's 2023. But it turns out S6 and S8 still, well, up to very recently, the only even spheres known to admit any non-trivial metrics. So what happened in the last 25 years? So what happened was that the odd dimensional case got completely resolved. So in the meantime, so what you can do is, if n is odd, you can use, well, okay. In general, the Ricci, the Einstein equation is some second order PDE, which pretty hard to solve in general. So what you do is you assume some extra structure. And usually the structures which have the most power are those that let you use methods of complex geometry, because then all the algebra magic happens, and it's usually pretty powerful if it works. So in even dimensions, of course, yeah, spheres usually aren't scalar, so it doesn't help you. But in odd dimensions, there's an analog of scalar manifolds called Sasaki metrics, which say, well, okay, a metric is Sasaki if the metric cone over the metric is scalar. And these things, I'm not expecting you to know a lot about them, but they let you use some methods of complex geometry, and they are very good at doing things. So they have been used to find examples in all dimensions. Yeah, so this is work of, well, maybe you should start with Boyer, Galitsky-Koller. This was 2005, who found metrics on all spheres of dimension 4m plus 1, which of course, together with the homogeneous ones, already exhausts all the odd integers. But of course, the homogeneous one, there's only one of them. So later also by Gigi-Koller. In 2007, they just found all of the odd spheres. Of course, S3 doesn't work, so. Yeah, many of these metrics, yeah, they even found some admitting continuous deformations. These come in large families. There's many. In odd dimensions, there's many and more non-trivial Einstein metrics on every odd dimensional sphere above S3. So in odd dimensions, both existence and uniqueness of non-trivial metrics are pretty much resolved. But in even dimensions, not much happened. So the only thing that happened in this time, in the even dimensional case, was a paper by Foscolo and Haskins in 2017. Who found another metric on S6. So this one, of course, you may say, okay, Böhm already found an infinite family, so what's so special about finding one new example? So this one was actually nearly scalar. So it has some special geometric properties, and it has a different isometry group. So all the Böhm examples, these are all invariant under SOP times SOQ, P plus Q. Is this the right one? Yes, I think so. And this one is, I think, SU2 by SU2. Yeah, so different isometry group, but of course, not a new sphere. So yeah, that's pretty much all the examples. So I can spoil you now and tell you what the theorem is we proved. So what we did is basically we pushed the methods of Böhm a bit and find, or maybe I should say, all of this is joined with Matthias Wink. And we found new metrics on S10. So we didn't go from 2 spheres unknown to emit non-trivial Einstein metrics to all spheres unknown to emit non-trivial Einstein metrics, but we went from 2 to 3, which, I mean, is also progress. But as opposed to Christoph's work in smaller dimensions, these do not come in infinite families anymore. So we found 3, and we're pretty sure that there are exactly 3. At least in cohomogeneity 1, there are exactly 3. Yeah, so the main goal of the talk will be to tell you a bit about how to make these, and well, what maybe some of the problems are. So how do you make Einstein metrics? So the first method is, of course, the trivial one. You just write something
Sorry,
down.
Jan, can I ask
Yes?
a quick question
Please,
before you
please,
continue? So how about non-standard Einstein metrics on, say, complex projective spaces? What's known there? Do you know? Do you remember?
Oh, this should be knowable. So, of course, in any given Kähler class, there's
Yes.
one. So it's equivalent to asking whether there are deformations of the Kähler structure, and this should probably be known, but I don't know off the top of my head.
Okay. Yeah, I should know, but I also don't know.
Yeah, I should have looked this up.
There's only one complex structure, right? Up to equivalence. That's okay. All right.
Okay, well then maybe it's also not trivial. Yeah, I think we looked for a second in cohomogeneity 1 and we didn't see any, but of course it doesn't mean anything. Cohomogeneity 1 is yeah, I mean, I don't know even whether we exhausted all the possible cohomogeneity 1 structures. I think we looked at one cohomogeneity 1 structure and didn't see one. Yeah, I don't know. Okay, so the trivial way is to just write one down, which of course most examples of Einstein metrics, you know, probably fall in this category, but there's a huge drawback, which is that if this isn't easy, it's usually impossible. So we can't really rhyme this. If the metric is in some non-trivial way dependent on the PDE, probably it's literally impossible to write it down in closed form, and then you're going to be out of luck. So the second one, I already alluded to this, is to try to use some rigid algebraic structure to help you. So I use algebra. And this is very, very powerful. Yeah, so in the Kähler case, existence is completely resolved. So existence is resolved. So, I mean, these are very famous theorems, but we should probably still talk about it for a second. Yeah, so if you have some Kähler manifold, where omega is the Kähler class, then the question of whether there is an Einstein metric which is compatible is completely solved. Yeah, so if what you have to do is you have to look at the first Chern class, which is a cohomology class in the second cohomology group. And you have your Kähler class, which is also there. And then you ask, okay, you look first, is the Chern class a multiple? If it isn't, well, no Einstein metric. And if it is, then if lambda is less than 0, lambda less than 0, this is equivalent to there being a negative Einstein metric. If it's 0, this is equivalent to there being a Ricci flat metric. which we will call Calabi-metric. And okay, if it's positive, then sadly this isn't equivalent. Would be too easy, but there is an extra condition, which is also of purely algebraic nature, which I will not explain. It's called K polystable. So this is equivalent to a positive Einstein metric. So very celebrated theorems. So the first two go back to the 80s. I wrote this down. So this one is Ober and Yao. This is also Yao. Famous, yeah, this is the Calabi conjecture. And the positive case is a lot more recent. This is 2014 by Chen, Donaldson, and Sun. Yeah, so in the Kähler case, the existence question is completely resolved. Of course, okay, whether you can actually check the polystability condition or not by hand is maybe a different question. But in principle, there are no PDEs here anymore. This is just, you check something on the manifold, and then either the answer is yes or it's no. But of course, there's a huge drawback, which is that, well, not all manifolds are Kähler. In fact, even most complex manifolds aren't Kähler. So for our problem, which was spheres, well, okay, S2 is Kähler, but yeah, that's it. Yeah, so this only works on very specific manifolds, and of course also only in even dimensions. And then, okay, in odd dimensions, I already told you a bit. Yeah, so in odd dimensions, the Sasaki thing is very strong. I will not talk too much about it. Yeah, so we have Sasaki Einstein metrics. They work very well. They can produce examples, many of them on many spaces, including all odd dimensional spheres of dimension at least 5. This is very good, but of course, it only works in odd dimensions. So what do you do if you're in even dimensions and your manifold isn't Kähler? Yeah, okay, so you're in trouble. So in general, well, it's a PDE. PDEs are impossible to solve. So you have to make some other assumption that makes it attackable. And okay, I'm giving a talk in geometry with symmetries. We're gonna assume symmetries. Yeah, so we assume enough symmetries.
Good that Yao wasn't so pessimistic as you regarding PDEs, you know, otherwise we wouldn't have all these theorems.
Of course. But I don't want to talk badly about people who are good at PDEs. I have the utmost respect, because for me, ODEs are hard and PDEs are impossible. And I'm very, very happy that there are people who think ODEs are easy and PDEs are plausible. Yeah, so go you. I'm afraid I'm staying away from PDEs. So in general, we're going to assume symmetries until the problem is so easy that we can solve it. Yeah, until there's a chance. So of course, the easiest thing you can do is you can look at homogeneous metrics. Yeah, so they can't really assume more symmetries than homogeneous. Okay, can only look at symmetric spaces, it's maybe even stronger. But so on spheres, of course, I already told you about Ziller's theorem. So on spheres, homogeneous Einstein metrics are classified. In general, even this is open. So it's not known which homogeneous spaces carry Einstein metrics and which don't. For some, there are positive results. For some, there are negative results. A lot are just open. There's no known condition. It's unknown. But of course, today we're interested in spheres. So on spheres, the homogeneous case is known. And the next most plausible is homogeneity 1. Yeah, so we go for homogeneity 1. So this will turn the PDE into an ODE. Yeah, so how does homogeneity 1 work? So you have your sphere. And okay, you have your group action, so there's going to be some principal orbit. And there's going to be 2 singular orbits, which, okay, may be points, may not be points. And it's going to project onto a closed interval. So in general, of course, the orbit space may be either a closed interval or an S1. But we know if there is going to be a positive Einstein metric, of course, it's going to have positive Ricci curvature. So it has to have finite fundamental group. So this doesn't work if the quotient has fundamental group. So it's always going to be a closed interval. And okay, what we can do is we can just pick a t direction on the quotient. And our Einstein PDE will become an ODE for this metric GT on the principal orbit at time t. Yeah, so over each time t here, you have some principal orbit. It will carry a metric. This metric will now solve an ODE. Okay, so this ODE is second order. So if we transform it into a system of first order equations, well, it's going to be twice as many equations as the number of functions which are in this metric on the principal orbit. Yeah, so we obtain 2 times the number of So depending on the homogeneity 1 structure, you can just look, yeah, how many degrees of freedom do you have in the principal orbit? You're gonna get twice that number of equations in your ODE. And it turns out, well, what's the easiest thing? Okay, the easiest thing is if the principal orbit is just a round sphere, you're gonna have 1 function and you're not gonna find anything, well, set. So the next easiest thing is if you have exactly 2 functions. So, okay, that's what we're going to look at. So we look at, well, what's our homogeneity 1 structure? We take SO, well, it's this. So this group acts on, well, D1 plus D2 plus 2. And you just take the induced action on the sphere. And this is going to be our homogeneity 1 action. So this will have principal orbit as D1 times SD2 in the middle, and the singular orbits. Well, what happens at one side is that the one sphere collapses and you have an SD1, and on the other side, the other sphere will collapse and you have an SD2. Yeah, this is just, well, you will look at the action. Yeah, one of the singular orbits is when here the first D1 plus 1 coordinates vanish, and the other one is when, oh, say when the first, yes, when the first part vanishes, and the other singular orbit is when the second half vanishes. Okay, so these are our homogeneity 1 actions that we're going to look at. These are not the only possible homogeneity 1 actions on spheres. You could also have, for example, a point on each side, and the principal orbit is a homogeneous sphere. So Sn but not homogeneous under the full group SRn+1, but say only SP1 times SP. Something like this. Yeah, another homogeneous sphere. You can look at metrics like this. Yeah, maybe you're lucky, maybe you aren't. Probably you aren't, but no strong statements on this one. So we look at the product action, which is homogeneity 1 with these orbit types, and we look for Einstein metrics here. Yeah, so what's good about this is that there are exactly 2 functions in this. Yeah, so on the principal orbit, the metric will always look like F1 G round on the first factor. So put a squared here plus some F2 on the second factor. Yeah, so you have 2 functions, which will give you a system of 4 ODEs. Get 4 first order ODEs. Yeah, these are obtained from doing Ricci of dt. Yeah, or let's say equals whatever d1. Yeah, lambda times the metric. You pick some Einstein constant lambda. Yeah, so this will give you equations for your functions. And then, of course, well, there are equations you haven't used. And it turns out all of those are equivalent to 1 extra equation. So you always get 1 extra equation, which is not a differential equation. It's just an equation which comes from constant scalar curvature. Yeah, so if you do this, you write down your equations, you're going to get 4 ODEs and 1 constraint equation. So, well, what do these look like? Of course, I'm not going to do all the calculations now for you because I'm not crazy. But I will say, well, you take this, you do some reparameterization, and you do some, well, you use the extra equation to eliminate one of the variables. And then I will actually draw this for you. Yeah, so if you eliminate one variable with the extra equation, you're going to get 3 variables, an ODE in 3 variables. So this should be drawable. Yeah, 3 dimensions. I should be able to draw your picture. So I will draw your picture. So what does this whole ODE live on after the reparameterization? It will live on something compact, and it will actually live on some cylinder. So you have some cross section which looks like this with 2 corner points, and it will live on a compact cylinder over this thing. Yeah, so yeah, so the slice here is something like S2 if you take just a quarter of it, say X. Yeah, so this is some, if you slice an apple twice in the middle, the surface of that, so which I will draw flattened times -1. Yeah, so this is the space that our ODE lives on now. And what are we looking for? Well, we're looking for a solution to this ODE, which is a solution, an integral curve to some ODE vector field, which collapses on both ends in a controlled way. And the nice thing is, if you do these coordinate changes, well, your vector field is going to have some zeros, which correspond to singular behavior. So I will draw you the zeros of the vector field. And the way the math turns out is that you can tell what happens geometrically to your solution just by seeing which of these critical points the curve goes to. Yeah, so you say you start on some principal orbit, you give some random metric. Let's use maybe a different color. So blue. So you start with some random metric on some principal orbit. You can solve the Einstein equation in both directions. It's going to do something. And in the end, it's going to end up at one of these orbits. So yeah, maybe I should say this. This direction is monotone. So it will always move from left to right. So we'll end in one of these critical points. And you can tell what geometrically happens just by what critical point it goes into. Yeah, so these 2 points here in these corner points, these are the generic behavior. So generically, if you fix some metric in the middle, you solve your Einstein equation, it's just going to become singular. Yeah, one of the functions will blow up, or become 0, and then you're just set. Yeah, so these are just bad singular behavior, one corresponding each to the functions becoming bad. Yeah, and this one as well. So these are the generic ones. And then you have 2 good ones on each side, which is, we should save this. So these are the good ones. So these are smooth collapse. So of course, the thing that you want to have happen, which is that one of the orbits becomes, one of the spheres becomes singular and the other one doesn't, and it all ends up as a smooth sphere. This also is some kind of singular behavior because one of the functions will be 0. But you can tell in this picture here, one of these points is a smooth collapse of the one sphere. One of these points is a smooth collapse of the other sphere. If you run into one of these points, you're going to get a smooth metric, no matter what.
So Jan, when you say smooth collapse, you mean that the derivative of the one going to 0 is like plus minus 1, something like that? Like
Yes.
in
So that in the language of these functions, that's the smoothness condition, is that the derivative is 1. Right. Yes. What I mean is that the metric you will get will be a smooth will smoothly extend over the singular orbit. Yeah. So the condition on the function is 0, derivative is 1. In this parameter space, the smoothness condition is it goes into this critical point. Yeah, it's completely equivalent, which is very nice. And you have, of course, you have the same things on the other side as well. And then there's one critical point left, which of course, well, if you paid attention, well, the singular points, I said, well, this is if one of the functions becomes bad. This is if the other function becomes bad. Of course, what happens if both of them become equally bad at the same time? And this point here in the middle, which will play a pretty big role, this is what we call a conical singularity. So this corresponds to the kind of singularity you get if you just take, so you take your G round plus G round. This is a metric on the principal orbit. And you just take the suspension, the spherical suspension of this. Yeah, so sine squared. So this will be Einstein in the middle. But of course, it will not be a smooth metric at the corner points. Yeah, if you take suspension, a suspension is only smooth if the link is a sphere, or at least say a homology sphere. So this thing has to appear somewhere because it's an Einstein metric with the right group action and the right principal orbit. And this singularity is this point in the middle. And of course, I just wrote down an Einstein metric with the right group action. So it has to be a trajectory in my picture. And it's just a straight line. Oh, that wasn't straight. So imagine this is a straight line from this point to this. This is the so-called, well, it's called the cone solution. And I know I just said it's a suspension, but for historical reasons, suspensions are cones. I know it. Well, I didn't get to make up the name, so this is how it works. So yeah, this special solution will play a role. And what are we looking for? Well, we are looking for a solution which goes from this point here to this point here. So the way it works is that, okay, this is the D1 collapse on the left side, and this is the D2 collapse on the right side. And of course, the other ones, yeah, this is D2, this is D1. And the one I drew, that's roughly what the round sphere looks like. It's just a trajectory from this critical point to the other one. You can write down everything. Yeah, this is the round sphere. And now we're trying to find a second trajectory that goes from this point on the left to that point on the right. So how? Yeah, good question. So let me tell you how. The trick is, okay, well, maybe it's not much of a trick. Yeah, so I'll draw the image again. So you have your cone. Your cone solution. Okay, so, well, what do you want? You want a trajectory that goes from one prescribed point on the left to one prescribed point on the right. So you just take the point on the left and you look at all the trajectories that leave it. So if you look at all the trajectories going out of this point, this will be some two-dimensional manifold. And okay, I will tell you, yeah, on the left, the trajectory that leaves the point in the boundary slice, it will go to this point, to this other singular point that corresponds to the cone. The one on the boundary will go up here, it doesn't matter. So what we look at is we look at how the interaction goes as this manifold approaches the center. Yeah, so what will happen is this will, at each time, this manifold will approach this center line at some angle, and this angle might change as you go along. Maybe, yeah, maybe not, maybe it does. We can't tell. Yeah, it will, whenever you take the slice with some, okay, so this direction is called H. So if you take the intersection with some slice, H equals constant, every trajectory that leaves this critical point will intersect the slice exactly once, and you're going to get some kind of curve. Yeah, just by the way manifolds work. Yeah, so along each trajectory, the H is strictly monotone. So every trajectory will intersect each slice exactly once. You know, one limit point lies on the boundary, and the other limit point is the center, which corresponds to this suspension solution. Yeah, so at every slice, you're going to get some curve like this. And whenever your trajectory passes to a point on this curve, this means that on the left, you came from the critical point of your choice, because that's the definition. Yeah, so far, basically just a reformulation of what it means to come out of the desired point on the left. And now, of course, you can do the same for your desired point on the right. And I will tell you the rotation will go the other way around. So if you do the same thing for the point on the right, now the limit point will lie on the left side, and the rotation will go the other way around. And now, of course, you may be able to see the proof strategy. If you can calculate how much this winding around the center, how much of this happens. Well, okay, what's an Einstein metric on the sphere? An Einstein metric on the sphere is one that comes from the left and enters the right. So it's just corresponds to any point on the intersection of these two curves. Yeah, so you have these two curves. One goes like this, the other goes like, say, this. And every intersection point will have both the correct behavior at the start and at the end, and you will have an Einstein metric on your sphere. Yeah, so if the picture would look like this, then you would have here one intersection and here one intersection. Okay, no matter what you do, one point is going to be the round sphere, because the round sphere is homogeneity 1 with respect to our action, and the other one isn't. Yeah, so this is the strategy. What do we need to make this work? Well, in fact, you don't need so much to make this work. So one thing you need to make this work is you need to know on the boundary slice. So when I draw this picture, on the left here will be h equals 1. On the right will be h equals -1. That's because h is actually monotonically decreasing along the ODE. So we put the ODE goes from left to right. So the h has to go from 1 to -1. So if you look at the h equals 1 slice, you need to know what this curve does. So that's one thing. One thing is you need to know, okay, so we do this intersection business here. Of course, we do this in the middle at h equals 0, because everything else would be less symmetric, and this is a symmetry seminar. So you need to know as you go from h to 1 to the middle, you need to know where the boundary point ends up, because of course, yeah, if this point just moves around here, then, well, maybe you end up with a picture that just looks like this, and then no intersections and no luck. So you need to know what happens to this boundary point. And the last thing you need to know is you need to know what happens to the direction you enter the center in. So you have this direction, and maybe here's this. So you need to know how this changes. Yeah, these are the three things that you need. And of course, if you put all these together, you're going to be able to calculate the winding of this limiting curve. Right, so if you have some limiting curve and you want to calculate, say, okay, what's the easiest way to measure the winding? You put some angular coordinate on this. You want to measure how much this goes around in total. Well, it's just fundamental theorem of calculus, right? So you need to know how much the total winding is at time 0. You need to know how much the outer point moves. You need to know how much the inner direction moves, and then you just integrate it out. So the nice thing is these are all quite possible. So let's just do a quick sketch. So the first thing, well, okay, this is just a question of the h equals 1 system. So this is now literally a 2-dimensional ODE. So you calculate the linearization first at the center point. Two things can happen. Either this thing here will be a spiral infinitely often, and anything happens here, I don't care. Of course, if this is what happens, you're just super happy, right? Because this means that if you do your business in the end, and this curve spirals into the center, and the other one, of course, then will also spiral into the center, they're just going to intersect infinitely often, and you're just going to be done and have infinite families of metrics, and everything will be nice. You can basically, if you know this, all the other steps, you can skip most of them. And it's very nice because this happens. So this spiraling happens, but only on specific dimensions. So if you're on Sn, and then it's between 5 and 9. So this is how Böhm didn't have this formalism, he did it differently, but this is why there are infinite families on these spheres. These are the infinite families discovered by Böhm in 1998. Yeah, so you calculate this just has a spiraling behavior. If you have two spirals that go in the different directions, they're going to intersect infinitely often. Each intersection point is an Einstein metric. You're done. But it just stops being true. So above dimension 9, this is just not what happens. So in dimensions 10 and up, this is just going to not happen, and you're going to have your directions that limits can come in. Okay, so then you can calculate your directions, and you know, you have your trajectory here. And okay, also plausibly, it may go like this. Sure, yeah, same direction, which is bad. Of course, yeah, if you have some negative winding at the start, it may end up at 0. But you can just write down the equation of this two-dimensional ODE, and you will see that on these axes, you're going to have monotonicity. So the ODE always goes like this. So you cannot have any negative winding in the beginning. Yeah, so it can go like this, or maybe it can go round this way, but it cannot go clockwise. Just can't happen. Yeah, you write down the equation of the ODE. Only goes in the direction of positive winding. Yeah, so this means that the winding at h equals 1 is going to be at least, well, it cannot be arbitrarily small. Yeah, so the worst thing that can happen is something like this. Yeah, there's a lower bound on the winding, which is good. So the lower bound you can actually get out of the equations is enough to do what we want. Part 2 is the most trivial. So you want to know what happens to this boundary point here. Well, you look at the equations, the boundary is invariant. And you have 2 points at the top, at the bottom, which correspond to explicit solutions. So you know whatever happens, the point on the right is going to end up still being on the right. Maybe somewhere else on the right, but it's still in the same half. That's good enough. Good enough for what we need. So this is completely trivial once you have the right coordinates. And the last one is actually also pretty reasonable because, well, you enter in some specific direction here. You want to know what happens as you move along the ODE. This direction is just going to solve the linearized ODE at this special solution. Yeah, so if you have this direction vector field, say x, then the vector field X will just solve the linearized ODE at this special solution, which I call the cone solution. Yeah, so you have this direction, it solves the linearized ODE. And now, well, okay, now the actual hard part comes out, right? You have the vector field solving the linearized ODE. You need to find out what happens to the rotation. Yeah, you know. So what you're gonna need in the end is that it's gonna be past the vertical axis. Yeah, because if you want these to intersect, they have to go past the middle at the bottom. So they have to intersect by topological reasons. Yeah, so well, what do? You have this linearized ODE, you put in the solution which goes exactly downwards in the center, you solve it to the left, and you see what happens. Yeah, this is in the paper, this is where all the estimates happen, and this is where the non-conceptual, where we actually have to do calculations and estimate some ODE, and the not fun part. But okay, it's an explicit ODE. It was possible. Yeah, you write it down. Literally, just by brute estimations, you can get this thing to rotate enough. Yeah, so it turns out in dimension 10, if you start going downwards in the middle, you solve to the left, it will rotate like this. And the minimal rotation you have at the start is to the left. So, of course, you know that at the end, it's going to still be to the left, just by ODE comparison. Yeah, and that's pretty much how you go. Yeah, if you know this, then it's just a topological winding number argument, which is, I mean, you have to come up with it, but once you write it down, it's the only thing that can happen. Yeah, so you now have these two curves that go both. So one starts at the top left, goes clockwise, crosses this vertical axis. One starts at the top right, goes counterclockwise, also crosses the vertical axis. And you just show that by topological reasons, these two curves must intersect twice. Yeah, so one intersection will be somewhere here, one will be somewhere here. You have found your new metric. Yeah, so this is how the proof goes. Yeah, so for each homogeneity one action. So of course you can do, what does it work? Yeah, you can do SO P times SOQ. Or let's say let's do the same now. So D1 plus 1, D2 plus 1. So for D1, D2, you have choices, right? So you can do 2, 7, 3, 6. For each of these, you will find one new non-round metric. You do some short arguments to see that they are pairwise distinct. You found 3 new metrics on S10. And yeah, I think that's as much as I wanted to say, and it's 12, so thank you very much.
Thanks, Jan. Excellent talk. Are there any questions or comments for the speaker? I do have one quick question. I mean, what fails in dimension 12? Is this winding of the...
Yeah, so let me talk a bit about what happens as you go up in dimensions. So you may expect, just because of the things that happened in dimensions below 10, so it used to be infinite rotation, now it's only finite rotation, that rotation decreases as you go up in dimension. And this is simply, it's just what happens. So you can do the same thing for S12, S14, S16, and the rotation will just be less and less. And it turns out that in dimensions above 10, or let's say in dimensions above 11, so I don't accidentally say something that isn't true. So starting in dimension 12, the linearized behavior is not enough anymore. So it won't be true. So the curve will go from here to here. So it will not be enough to go around. So this is a plausible image. But of course, what's also a plausible image is this. Yeah, from the linearization, these two are the same. Yeah, so well, what's going to be true is that in higher dimensions, you will not be able to prove with these linearized methods that they are metrics, because I mean, you run it through a computer, the linearization, it's not enough. But the right picture could still happen. And in fact, for a while it does, and then it stops. So I can tell you, yeah, so the conjecture is, at least in cohomogeneity 1, there should only be finitely many spheres, that even dimensional spheres emitting such metrics. In cohomogeneity 1, I will not conjecture anything about in general. Yeah, and after S10, some will look like the second picture, and you're gonna have actually 2 instead of 1, and then these are just gonna separate out. And of course, once they separate, you're gonna have nothing. Yeah, so this is the conjectural picture, but of course, even if you know the picture looks like this, to prove it, it's entirely a non-linear phenomenon, right? You can't see anything in the linearization. And it turns out non-linear phenomenon means difficult. Who would have known? Yeah, so that's can't prove that yet. It's not in linearization. Yeah, feel free to prove it. Yeah, and on S4,
Jan.
I don't know anything. I can't even conjecture what happens on S4. Yeah.
Any further questions?
Thomas here. I have a quick question about what you just said about the conjecture. Do you only make this conjecture for SON times SOM, or in general cohomogeneity 1?
So for this cohomogeneity 1 action, the SO times SO, I'm 100% sure. So there it stops. It stops after either after S14 or after S15. It just stops. So for this action, I can tell you for sure. Then there are other actions that we checked. So if you have, if the principal orbit is an odd dimensional sphere with the unitary action, the homogeneous unitary action, where both singular orbits are points, there's also nothing. But we didn't check well, there's of course the list of cohomogeneity 1 structures is finite on spheres, they're known. But some of them have many parameters. So if the principal orbit is S4m plus 3 with the SP1 SPN action, then there's a bunch of parameters that you can have on the principal orbit. And I can't rule out that you may find in, for example, in this system, that you may be able to find some. So the conjecture for the specific cohomogeneity 1 structure, I mean, I'm very firm about that one. The conjecture in general cohomogeneity 1, I would also conjecture this, but I'm less than 100% on that one. In general, yeah, there may be some cohomogeneity 1 system where you manage to find metrics. I'm not aware of any. So there is another one on S8 where the principal orbit is the correct action that comes from the octonions. But of course, S8 is also already on the known examples of spheres. Yeah, but in higher dimensions, I think homogeneity 1 probably stops. The question of whether actually rigidity kicks in and on high even dimensions there actually is only one is completely up to speculation. I wouldn't wager to make a bet either way. But of course, homogeneity 2, everything starts becoming PDEs and everything is impossible now, at least for me. So it's very, very hard to say what actually happens.
Thank you.
All right, thanks, Jan. Let's thank the speaker again for a great talk.